Welcome to today's webinar, Debunking Ceramic Myths and Discovering Productivity. My name is Beth Greenleaf, and leading the presentation here with me today are Martin Dilliman.
Hello.
And Aaron Allen.
Hello.
Martin is the Engineering and Applications Global Manager here at Greenleaf. Aaron is an applications engineer and a member of our tech team. I'm a photographer and marketing specialist. We're talking to you from Greenleaf Corporation headquarters here in Sagertown, Pennsylvania. Greenleaf Corporation is a third-generation, family-owned American manufacturing company with plants in Pennsylvania and North Carolina and sales offices in China and the Netherlands. Greenleaf is a leading developer in cutting tool technology, specializing in the manufacturing of high-performance tungsten carbide and ceramic inserts, as well as innovative tool holding systems. Greenleaf continues to build on 80 years of innovation, which centers on supplying customers with productive solutions to every metal cutting situation. Today, we will be delving into some of the most common myths in the industry about ceramic tools, addressing 7 total myths. After taking a look at those myths, we'll take some time discussing what materials ceramic tools tend to perform the best with, and then we'll have some information for you about optimization methods, tips, and tricks that can help you get the most from your tools when machining with ceramics. At the end, we'll have time to open the floor to some questions, so make sure to stick around. Our first myth is one that tends to cause a lot of concern, especially for people who are seeing ceramic tools run for the very first time. It isn't uncommon at a trade show to have a passerby approach us, concerned about the sparks that they see flying into the machine wall, which begs the question, Aaron and Martin, is sparking always a bad sign when you're machining?
So when you're machining, sparking can definitely be a sign that something isn't right. However, when the process is optimized with ceramic tooling, what you are actually seeing are red-hot chips, not sparks. Sparking can still be a sign that something isn't right, but the red-hot chips you are seeing are no cause for concern.
All tools actually generate heat during the shearing action to remove material. Carbide tooling uses coolant to help control this heat. Since ceramics have a much higher thermal capacity than other cutting tools, they resist retaining the heat in the tool that could lead to failure. Ceramic tools actually thrive in situations with higher heat generation. The higher levels of heat removed in the chip is what you see in those bright sparks that are flying.
Our next myth is something that has historically caused concern regarding the use of ceramic tooling in general. And it's the belief that ceramic is such a brittle material that it isn't effective for use in inserts or end mills. Martin, can you tell us a little bit about that?
Well, 50 years ago, this may have been true. It's true that ceramic materials can be more brittle than carbide, but it's important to note there's been a lot of advancements over the past few decades in the field of ceramics. This in addition to the machining equipment used and the tool holders that have better capabilities. Innovative methods for strengthening the material with the addition of whiskers or other compounds, along with the rigidity of the tool holders and the machines, this helps reduce the forces and vibrations that increase the potential for the tools to break. The ceramics on the market today have been toughened and reinforced to the point where they are extremely reliable. There shouldn't be a fear of inconsistent tool life or random failures when they are properly applied.
There are several methods to combat brittleness commonly being used in the industry. The methods we will be discussing today include the introduction of whiskers to the material, phase toughening, and cutting tool geometries. Aaron, do you think you can start us off?
Sure. So the first method is the addition of whiskers made of silicon carbide. These are referred to as whisker-reinforced ceramics. They're composed of a hard ceramic matrix reinforced with extremely strong, stiff silicon carbide crystals. These whiskers act like rebar in cement, adding tensile strength and improving the fracture toughness of the brittle matrix. These whiskers are grown carefully under controlled conditions, and due to their high tensile strength, the whiskers redirect any potential cracks, forcing them to move along the whiskers. This requires a huge amount of energy, which helps to halt the cracking process. Alternatively, this could force the whisker to be pulled out of the matrix, but that also requires a huge amount of energy, If the crack doesn't have enough energy to pull out of a whisker, it will actually cause the whisker to elastically deform in tension. And once the force is removed, the whisker under tension will actually bring the two planes of the crack back together. This serves to decrease the brittleness of the material itself.
Another method for combating brittleness is a process known as phase toughening. This is used in our Excitant 1 grade. Through the manipulation of grain growth and phase distribution, the ceramic material attains an internal matrix of interlocked grains. That, along with the properties of the base material, this grade is capable of resisting deformation and growth of cracks in a variety of materials and machining environments. This phase toughening process is proprietary to Greenleaf and allows for a ceramic grade capable of feed rates similar to that of those typically used for carbide inserts.
We can also further combat brittleness through things like cutting tool geometry, allowing the ceramic tools to hold up better in their applications. This allows for ceramic tools to function with a lower chance of failure through altering the forces that would normally cause them to fail in a tool. A great example of that can actually be seen in our Excitant 360 end mills, which have a unique flute design that minimizes the cutting forces and reduces the vibrations. This, along with the phase toughening, can help to minimize the risk of the tool and improve your overall productivity.
It is important to note that during the cutting process with ceramic tools, the heat that's generated as a result of the compressive strain and friction, the heat helps reduce the strength of the material in the shear zone and results in lower cutting forces. It's important to handle ceramics with care though. Don't just throw them in a toolbox. It's important to take care when indexing the inserts also. If you over tighten the clamp screw, it could potentially cause cracking. As long as you're following the torque spec of the tool holders and the cutters, there's no fear of breaking inserts.
Thank you both for all of that information on how the industry is combating brittleness in ceramic tooling. Our next myth is somewhat related. We all know that carbide can be reground, but when it comes to ceramics, I've heard it said that they need to be discarded once they chip. Is this true, guys?
Something kind of cool about ceramics as a material is that even when they chip, doesn't necessarily mean that the tool stops cutting, because underneath rock there's more rock. This means that you can sometimes continue to cut with chipped ceramic tools as it's equally as hard and tough on that new surface. However, in cases where the chipping needs to be addressed, there are still some options. Ceramic inserts can actually be refurbished as well using a similar process and giving a new lease on life.
Making sure to set up a process that has consistent wear always allows for maximum regrinding opportunities. You don't want the wear to be excessive to the point of failure. This will not allow for any regrinding opportunity.
While ceramic end mills cannot be reground in the same way that carbide tools can, they can be resized. It is important to note that it reduces the overall length, but it does restore the function of the end mill.
That's true, but in the case of our new product, Capstone 360, you do not look for wear in the same way you would with carbide tools. Instead, you wait till the sound of the machining changes or you see a sudden spike in the spindle load. As long as the chips are generating the same color, you can assume that the machining's properly set up.
So what makes Capstone 360 different from traditional ceramic tools?
So with our new Capstone 360, it has a ceramic tip that's attached to a carbide shank, and it allows for the speeds and feeds capability of ceramic while having the rigidity of a carbide end mill. And it's used to perform in high temp alloys like Inconel and other cast irons, and performs very well in those materials.
The next myth I'd like to bring up deals with the application of tools rather than the nature of the material itself.
I've heard ceramic tools can be used with the same parameters as carbide. Martin, what are your thoughts on this?
Well, a common mistake people make, and we get a lot of calls on this into the tech team, is that people can just plug a ceramic insert into their pre-existing carbide tooling and work with the same program and expect it to work properly. This will result in poor tool life and probably make you question why are you even trying ceramics to begin with. Ceramic tools need to be applied using a different set of feeds, speeds, strategies, and tool paths in order to have the best results. If you aren't taking these into consideration when you're switching from carbide to ceramic, you will not see the increased productivity that you should see. Focusing on speed and feed to balance the chip thickness is extremely critical for ceramic machining. Focus on the entire process, including rigidity of the machine and tool holding, are important for the ceramic tools to be used to the best of their abilities. We'll cover more on the specifics of this later when we discuss optimization.
Our next myth deals with one of the factors that can cause initial hesitance when looking at switching from carbide to ceramics. Ceramic has a shorter tool life and is more expensive than carbide. How true is that, Aaron?
This can be argued to be true if you're exclusively looking at how many minutes of cutting a tool provides you with, and if you're only viewing the upfront cost of ceramics versus carbide. Ceramics do tend to have a higher initial cost than their carbide counterparts and may not last for as much time as a similar carbide tool. Tool life, however, should not be measured in how much time a tool is functional for, but rather how much material is removed in its lifespan. When they're being used at proper feeds and speeds with appropriate materials, ceramic tools often remove more material per tool than carbide. Using this definition of tool life allows us to judge the tool's effectiveness instead of how much of its time it'll use for you. It is also important to bear in mind when you're considering the overall cost difference between ceramic and carbide. While ceramics may be a bigger initial investment, the increased metal removal rates over a shorter period of time reduces the overall burden rate, increasing your machine's capacity without additional costs over time.
In a similar vein as our last myth, our next myth also has to deal with the cost of ceramics, but focuses more on specially designed tools. It's been said that specially engineered ceramic tools are not worth the added investment. Martin, can you tell us a little bit about custom tooling and if you think the investment is worth it?
Of course, I think the investment is worth it. Custom tooling provides manufacturers with flexibility for productivity gains. It's important to know that they don't have to settle for only standard catalog solutions. Specialized tooling can help improve the entire production process. Our goal is always to help find and simplify operations for manufacturers. Custom tools could be something as simple as increasing the diameter of a milling cutter and to allow for just one pass versus multiple passes. Or, on the other end of the spectrum, it could be a complete special form cutter that includes special insert designs along with a total complete special tooling package in order to help shorten the overall manufacturing process for our customer. Tooling needs do differ for every manufacturer, and if a standard catalog tool isn't available and can't meet the needs of the customer, that's when a customized option is best.
That makes sense. Everyone's machining needs definitely vary a lot from shop to shop when it comes to custom tooling. What are some of the ways that custom tooling can increase productivity and save money? And what sort of manufacturing would that be relevant for?
Well, custom tooling solutions, especially ones that combine multiple operations into one tool, provide increased productivity for manufacturers. The time savings and improved quality are two of the biggest benefits. If a custom tool could cut out an operation or reduce the number of setups for a part, it adds to the total productivity for the production run. Manufacturers who have high volume production often benefit the most from custom tooling. Even small gains in productivity can yield huge results for a customer. It can help them meet their takt time requirements and deliver better quality. The return on investment for a custom tooling solution is easily justified by the long-term savings that can be achieved versus a slower process with standard tooling. Custom tooling often makes a difference in quality as well. Developing tools and inserts per the part geometry can lead to improved surface finish and overall part quality. If a machining process requires changing between multiple tools during the operation in order to achieve the part geometry, it can lead to mismatches and poor surface quality. This can be eliminated when a custom designed tool is applied. By using a design with all inserts engaged during the same cutting process, the tool pressure is balanced and can yield better results for high quality surface finish. Another major consideration to keep in mind when it comes to custom design tooling is the cost to produce. Producing specialized tools does require more engineering time and possibly more extensive manufacturing processes compared to what you'd find in standard tools. This results in a higher price point. However, the extra cost is easily offset with the time savings and quality improvements that can be added to the customer's productivity.
Special engineered or custom engineered products are actually a visible strength of the Greenleaf product line. Customers from around the world utilize the Greenleaf engineering services to address their specific and often complex requirements. You can find our special tool design information checklist online at our website. Our next myth focuses a bit more on the effects that using ceramics has on your machine. A lot of people have concerns that ceramic tools stress the machine to a far greater extent than carbide. What do you think about that, Aaron?
So one of the most important things when running any tool in any machine is not to exceed the parameters of the machine itself. Running a machine within its higher allowed limits shouldn't be an issue, considering that's what the machine is rated for. It is true that running at higher speeds may wear out the bearing of the spindle slightly faster than the running tools at lower speeds, and ceramics tend to run at higher speeds. However, you are also getting more productivity for the duration of the time that the machine is being run. Much like how we should consider tool life to be the amount of material removed by the tool, we should also consider how effective your machining is when looking at the life of a machine. At the end of the day, you are likely still saving money if you are using ceramic tools properly to gain the increase in productivity that they can afford, even if using the higher speeds available result in a little more wear on the machine over time.
Thank you both for clearing up those myths. Now that we've made it through some of the most common misconceptions on ceramic tooling, let's start talking productivity. First, I think it would be beneficial to discuss what materials are best for use with ceramic tooling. There are actually very few materials that aren't machinable using ceramics. It's really more a matter of whether or not ceramics can provide enough benefit in your operation to justify the higher initial costs. That being said, ceramic tools can be used and provide value in almost every industry. Martin, can you expand on that for us?
Well, it's true. Ceramics perform their absolute best, especially when applied on specific materials. These materials include a wide range of cast irons, hardened steels above 45 Rockwell C, and heat-resistant superalloys. The hardness of the material is one of the first key properties that we consider when looking at applying ceramics. When considering what tools to use with your material, it's very important to remember that within ceramic tooling, the grade matters. There are many factors to consider when selecting a grade, including the machine, the work holding, what type of operation you'll be performing, and what goals you're trying to achieve, whether you're looking at improving cycle time or longer tool life. Our team of application engineers are always happy to help provide some general recommendations regarding which grades to apply based on the type of materials. It'd be great to say that ceramics can machine anything, but there are some materials that it's just too hard or too abrasive for ceramics to work effectively when applied. This includes materials like carbon fiber, since the shearing of the material is different than that of metals. Other materials like fiberglass technically could be cut with ceramics, but are not the most cost-effective method. If you're looking at machining cast iron materials, you can apply all of our ceramic grades, but it is dependent on the type of cast iron you're machining. A lot of our ceramic grades can be utilized for cast iron turning and milling applications. The primary ceramic grades for maximum productivity are our GSN 100 and Exciton 1. The GSN 100 is a hot press silicon nitride grade, which offers outstanding tool life in cast iron machining at speeds up to 5,000 surface feet. This grade works exceptionally well in multiple cast iron applications and may be one to look at if you're looking to maximize productivity for your cast iron machining application.
For hardened steel machining, you can apply our black alumina, Gem 8, our whisker reinforced WG300 or WG600, or our phase toughened Excitin 1 grades. We have great success turning hardened steel alloys with WG600. This grade offers the ability to rough, semi-finish, and complete finish passes. All of these grades help the customer gain productivity with significant increase in speed versus carbide grades. It is also important to note that we offer standard tool holders that are made for turning applications. The rake angles on these holders are different, which helps promote longer tool life for ceramic inserts than in a carbide tool holder.
Improved productivity from machining of heat-resistant superalloys or high-temp alloys is one of the ways Greenleaf gained popularity when WG300 was introduced in the mid-1980s. During the cutting process, these materials require high strain rates which cause the material to fail without going through plastic deformation. Balancing heat while machining, especially in milling of HRSAs, is key to achieving regular wear with ceramics. More brittle, less ductile alloys tend to be easier to optimize parameters since the chip control and heat are easily predicted. It is important to remember that once optimized, ceramics can reduce cycle time, which leads to less WIP, work in process, or reduce or eliminate grinding, EDM, or ECM processes. When machining superalloys, we recommend silicon carbide whisker reinforced ceramics or our phase toughened ceramic. It can be said that our ceramics like to eat that Inconel up.
They certainly do, Martin. They certainly do. When it comes to getting the most out of your ceramic tools, optimization is key. We'd like to take some time now to discuss some avenues to get the most out of your ceramics. Within this section, we'll discuss the equilibrium between the generation and evacuation of heat, how you can use chips and chip thickness in particular to tell you what you need to change in your operation, and we'll take a look at what you can learn by viewing the different kinds of wear that occur on ceramic tools. Then we'll have a couple of general tips and tricks for you all. Let's start with heat generation and evacuation. Aaron?
More than anything, optimizing ceramic tooling involves finding the right balance between heat generation and heat evacuation. Heat is generated during the machining process with ceramics through a variety of actions. One of these actions is chip formation, which will cause material to fail in a combination of shear and tension. It also includes the heat being generated by friction between the chip and the cutting tool. Finally, the heat is also generated by friction between the cutting tool and the workpiece. This generated heat is then dissipated away from the cutting tool cutting zone, with a higher majority of it staying in the chip, where only a very small amount of it gets conducted into the workpiece and in the tool. The highest temperature in a metal cutting operation is typically seen right at the very edge of the cutting tool. It is very true both in the case of tungsten carbide and ceramic tools. The main difference between them is how high the temperature can be. Unlike carbide, ceramics retain their high strength and hardness at temperatures exceeding 800 degrees Celsius. This allows for the much higher cutting speeds that are a hallmark of machining with ceramics.
Next, we'll be discussing chip thickness and its role in optimization. You can tell a surprising amount from looking at your chips. Martin, can you give us some tips on how we use chips?
Of course. Chip thickness is particularly important in ceramic machining because of its role in the distribution of heat. As we've mentioned, balancing the heat is critical for any ceramic machining operation. The thinner the chip, the more heat is potentially transferred into the tool or the workpiece. If the chip is too thick, it may actually act as a heat sink and draw too much of the heat away from the shear zone. In turning, chip thickness is a function of the feed and the lead angle of the insert. It's important to know that when cutting with a round insert, the lead angle will vary by the depth of cut. In milling, however, it's additionally affected by both the axial and radial engagement or step over. Calculating and understanding the average chip thickness is very important to us. This is the best method we have to judge how much heat is absorbed by and evacuated by the chip. Maintaining an average chip thickness leads to the best control of the steady state of heat from generation to distribution to evacuation. A good rule of thumb that can be used for all ceramic turning of ductile materials is as follows. Once you've determined the optimal cutting speed and chip thickness for a given grade and insert in a specific material, you can then vary the speed and chip thickness proportionately up or down as required. Adjusting parameters higher is dependent on the limits of the cutting tool, the machine, and the fixturing of the workpiece.
That's a lot of information just from the chip. Thanks, Martin. If in doubt, the Greenleaf catalog is an amazing resource available to you. It specifies the calculations required to determine chip thickness and other parameters. You can find it online on our website under the catalog section. Our next topic for optimization is wear. You can tell a lot about what you may need to change in your program or application by looking at the wear on your ceramic tools. The kind of wear that tends to happen is different for ceramic and carbide. For example, ceramic tools tend to be more chemically stable at higher temperatures. This means that chemical wear, which is a major problem for carbide and a large part of the reason that we tend to use coating on carbide tools, is less of an issue with ceramic tools. Aaron and Martin, can you expand a little bit on some of the wear that you might run into with ceramic tooling and what it means?
Sure. So the first type of wear we have is flank wear and edge rounding, and it's otherwise referred to as regular wear. It is the best kind of wear to have. It means that the machining process is stable, the stresses are carried out well, the heat distribution is neither too little or too much in either the tool or the workpiece, and the tool is being used up as efficiently as possible while material is being removed.
This next image shows chipping. Chipping is often a result of vibration or instability, and it could mean that the tool is encountering large inclusions along the cutting path that are different or harder from the rest of the base material. Chipping leads to the uneven distribution and of mechanical stresses and heat along the cutting edge and can lower tool life. Prolonged chipping may lead to our next type of wear, flaking.
This image of flaking shows that it's a more severe version of chipping. This may indicate the speed is too low to reach optimal strain rates and plasticization, or the chip thickness may be too high, which would result in excessive mechanical stress and too much heat leaving the cutting zone with the chip. Prolonged flaking may lead to top slicing.
Here you can see an example of top slicing. This occurs when the mechanical stresses parallel to the surface of the tool exceed the transverse rupture strength of the cutting tool. This is generally a result of excessive chip thickness combined with speed that is too low or too high. Reevaluate the cutting path to rule out any sudden increase in chip thickness and reduce cutting conditions, particularly the feed rate.
And here pictured we have flank slicing, and it's usually a result of impact that exceeds the toughness and transverse rupture strength of the cutting tool. Flank slicing is also an end case of existing irregular wear and excessive speed. To counter it, try switching to a tougher ceramic grade like Excitin 1. You can also try lowering the cutting speed and once again make sure everything about the cutting path is smooth as can be.
In this image you can see chemical wear. Chemical wear is the least common provided the material being machined is correct for the tool. It occurs as a result of chemical interaction between the tool and the workpiece at elevated temperatures. It is expressed as crater wear on the rake face and aggressive flank abrasion and striations. Reducing the amount of heat can be somewhat helpful, but the cutting tool and workpiece material incompatibility may ultimately mean you need to use a different cutting tool.
In instances where mechanical abrasion, which is pictured here, is the primary wear mechanism, the flank of the insert looks like it's been ground up by the workpiece after a short time in cut. The composition of the material being machined is more likely to have more strength and hardness variation between the material's main phases. The hardness of the cutting tool may not be sufficient compared to the micro hardness of the certain phases of the workpiece material. This could result in too much heat being retained in the cutting zone, thus causing the extreme abrasive wear. Another option is that there is actually aggressive chemical wear, which can resemble mechanical abrasion.
Our next kind of wear is notching. This is a thermal mechanical type of wear. It's a special case of mechanical abrasion that occurs when the surface of the machine material exhibits heavy strain hardening, also known as work hardening, or when a hard scale is present on the outer surface. Since the hardness of the surface layer is higher than the hardness of the material deeper in the cut, this can lead to higher heat generated in the portion of the cutting zone at the surface. During the cut, this increased heat generation can soften the cutting tool that results in heavier abrasive wear in that location on the insert. The wear further increases as heat is generated in that area, which continues to amplify the effect. Straight edge inserts are generally more susceptible to notching than round inserts, though lead angle can play a strong role in the development of notching. The lower the lead angle, the more likely it is that there will be notching. Lower speed and higher lead angles, or lower depth of cut with round inserts, can reduce notching.
Next wear is crater wear, and it's mostly a case of mechanical abrasion. It occurs as a result of the hot, heavy, and extremely abrasive chip impacting the rake face of the insert. This can be more common when machining with materials like Excitant 1, since it is usually applied at much higher chip thickness than aluminum oxide-based ceramics. Unless the crater wear is very aggressive, which would then more likely be chemical wear, it is a manageable wear pattern, increasing the feed while reducing the depth of cut. If chip thickness should be preserved with a round insert, would move the crater farther from the edge, not compromising the strength and toughness of the cutting tool. Reducing the speed will also reduce the rate at which the crater forms.
In this last image is the worst kind of wear. It's fracture, also known as catastrophic failure. It happens when the ceramic tools are grossly misapplied. It is important to note that even when grossly misapplied, Excitant 1 will likely not fracture, but will instead show heavy top slicing that has a deep notch-like appearance from the flank of the insert. This still allows for the ceramic to remove material, despite the damage that may occur to the insert.
Thank you so much, guys. It's really interesting how chips and wear can give so much insight into what is going right or wrong with your application. On the topic of optimization, as we said earlier, ceramic tools require a bit of a different approach from traditional carbide tools. The gains you stand to acquire from ceramic cutting tools are substantial, but they do require time and effort. With that in mind, there are some general application guidelines, tips, and tricks that can make the application of your ceramics a bit easier to approach. Aaron, what advice do you have for us regarding creating synergy between tools, tool holders, and your machine?
The only true requirement when working with ceramic tools is higher RPMs. However, depending on the grade of ceramics, some can even be ran at the same speed as carbide. As previously mentioned, ceramic tools can be quite versatile in the materials they can cut, depending on what machine you have available to you. However, that does not mean that having a slower machine completely rules out using ceramic tools. Instead, you can look at other ways to optimize the relationship between the tool and the machine. Using a machine that features slower speeds may mean you just need to use a larger tool. Rigidity is paramount when machining with ceramics. Try to run as short of tool hangout as possible, as reducing vibrations and chatter will help protect your ceramic tools.
Excellent. Is there anything in particular we should know about when it comes to ceramic tool holders, Martin?
It is vital to ensure you're using the right tool holder and seeking to minimize the tool length for deflection purposes. Tool holders designed for ceramic inserts differ from those designed for carbide, and different manufacturers may approach this in different ways. Because of the differences in the designs, they could lead to problems that may affect your tool life. The tolerances and shape of the tool pocket and shims used may differ between ceramic and carbide tool holders. This may lead to incorrect insert height as well as incorrect distribution and transfer of cutting forces. The combination of rake angles and positive positioning of the insert in the pocket are extremely important. Rake angles that are used on carbide tool holders may not be optimal for ceramic machining and should be reviewed if poor performance is seen when applying ceramics. Any of these may lead to irregular or possibly catastrophic failure on their own. When put together, poor tool life is almost guaranteed. With that in mind, tool holder design is critical for ceramic inserts, and we recommend using tooling designed for ceramic inserts wherever possible. Additionally, you should seek to use integral tool holders for maximum rigidity. Modular tool holders may add flexibility for usability in multiple operations, but they also add a degree of freedom that can increase the potential for deflection and additional vibration. You should always ensure that you have checked your tool holder for runout before using. You want the runout to be as low as possible.
Thank you so much, Martin. Are there any other major considerations to bear in mind when working with ceramic tools, Aaron?
Yeah, so one of the biggest failures that we see with ceramic tools is not actually regarding the cutting tool itself, but rather the effects of chip wash. We've seen chip wash collect over the steel clamps and the hot chips erode the steel. We recommend actually putting a carbide plating on these clamps to help moderate the effect of the chip wash. Mechanical chip breaker shims can also be integrated between the clamp and the insert to reduce chip wash on the clamp. And additionally, we have different ceramic edge preparations that can help redirect cutting forces and aid in chip management. Martin, would you be able to tell us more about ceramic edge preparations?
Of course. With ceramics, it's vital to ensure that you're using the correct edge prep. Unlike tungsten carbide inserts that typically have a honed edge and can utilize chip forms to control chips and the edge strength, ceramic inserts commonly require a chamfer or a land put on the edge. Some applications with ceramics may not require a hone. The hone is applied to ceramic tools for the same reason as applied to carbide. It's a method to help protect the edge from microchipping. The microchipping can lead to an uneven buildup of heat and stress distribution along the cutting edge. The edge prep on ceramic inserts is meant to change the direction of the forces to direct them more into the insert. By increasing the size of the land, along with the appropriate feed and depth of cut, it will direct the cutting forces into the thickest portion of the insert instead of along the flank edge. Determining the appropriate edge prep is critical for optimizing the operation of ceramic inserts. A small change in the land or on the hone can make a significant difference in performance. Tool life or possible increase in cutting parameters may be possible, but require testing and analysis. Selecting the appropriate edge preparation for the given combination of workpiece material, type of machining, and cutting tool material is paramount to the stability of the machining process and for optimal tool life.
Using the correct grade is also very important when machining with ceramics. This is very dependent on what material you are machining and what process you are engaging in. For a full overview of our grades, take a look at our catalog. The magnitude of the stresses that an insert is able to carry without failing are not only material dependent, but also directly related to its geometry. The thickness, shape, and corner radius of a tool all play an important role. Ceramic materials with higher strength can be applied in more fragile configurations, like straight edge. Optimizing your machining strategy and tool path are vital and can vary greatly. If you have any questions about the applications of your Greenleaf ceramic tools, you can always reach out to myself or another member from Tech Team via our email under Contact Us on our website, or call in to our main office and ask for technical assistance to help figure out the best way to optimize your tools for maximum productivity.
Thank you both for all of your time and for sharing your expertise. And thank you for sticking with us. Ceramics sometimes get a bad reputation in the machining world, with myths about them running rampant. However, through looking deeper into some of these common myths about ceramic tooling, it becomes clear that when used properly, ceramics have an important place in manufacturing. When using the correct grade of ceramic for your material and operation and optimizing your usage, ceramics can give you huge gains in productivity and a reduction in the total cost to manufacture. If you have any questions or need advice on using your Greenleaf tools, we have our catalog available on our website. It's a great resource and may be able to answer a lot of your questions or concerns about ceramic applications. If you have specific questions or are having trouble, we always recommend giving our team a call. We'd like to open the floor now to the viewers for any questions you may have.
What kind of parameters and materials are recommended for Capstone 360?
So we'll start with materials. We mainly recommend them for HRSA materials like Inconel 718 and some good starting parameters for like 45 Rockwell material would be about 1,300 surface feet and 1,002 per tooth. And we recommend usually about a 30 thou depth of cut at 80% step over.
Great, thank you. We have another question here. If I wanted to test ceramics in my shop, how or who do I contact, and is it possible to get a demo done?
It's a great question. So we have a large sales force that sell direct, also work with a number of distributors as well. So any person looking to do testing can reach out through your resources to try and contact Greenleaf directly. They can also reach out to us directly here at our corporate office in Sagertown, Pennsylvania, via email or call the 800 number as well. That's located on our website. So reaching out, we can arrange to connect you with the technical sales team to help run any type of demonstration needed.
Wonderful, thanks. Now, we have a question here about the age of machines. Do ceramics work on machines that are over 10 years old, and do I need to have a high spindle speed?
Although older machines could have a tendency to have a little more issues with maintaining location or possible run out, that may make it a little more difficult to help optimize with the ceramics. Although being able to apply a variety of different grades, we can try and optimize to come up with the best solution possible. Again, it takes a little bit of demonstration working with our sales team or the applications team here to help figure that out, but can be done in most cases. Regarding the high-speed spindle, it's not necessarily a requirement. We do look at speed primarily, though, to make sure that we will have enough heat generated in the cut. So that speed requirement would depend on the diameter of the tooling or the diameter of the workpiece that's being used.
Okay, great. Thank you. Does ceramics work for milling and turning operations as well?
Yes, so it depends on the grade. For instance, with our Gem 8 grade, it's far too hard to mill with due to the natural of the interruptions comes from milling, but it works excellent in turning of hardened materials and cast irons. But with the milling, you have great grades for that. You have Exciting 1 for, first choice in milling. It's the toughest ceramic we have. And then we have WG 300 and 600 that also work pretty good for having a little bit more wear resistance when it's needed. And then we also have GSM 100, which works better in the cast iron materials. So we have quite a few grades to try out different machining operations. So there's that.
All right, great. And we have a bunch more attendee questions coming in here. So let's move on to this one. Would you have any suggestions to avoid or prevent the chances of chipping of the ceramic tools?
Yeah, I think Aaron addressed that a little bit in the presentation there, but typically chipping comes from a vibration that may occur in the operations as well. So helping to reduce any chance of vibration will improve the potential tool life of the ceramic inserts. So finding ways to have more rigid tooling also on the workpiece itself, if additional fixturing or clamping may help prevent any type of chipping you may see.
And any kind of inclusion differences, different grain sizes and stuff. Hard spots and soft spots, I can do it too.
Okay. And we have a question here. An attendee's asking if you could mention the production of ceramic cutting tools. So talk a little bit about that.
I'm not quite sure what the question is. The ceramics themselves are a pressed product. We have the whiskers that are produced that are mixed into the matrix, and then they are pressed for being produced into inserts. I'm not sure if that answers the question fully or not, but.
Okay, yeah, thank you. Now, we have one here. Is ceramic recommended for machining titanium? And if so, which grade?
So we've tried machining titanium with ceramics with very little success. It's just one of those materials that's quite tough on the tool, just chemically. So once you heat it up past the flash zone of titanium, it'll start chemically interacting with the ceramic pretty violently. And like the chemical wear slide that we saw, it'll start forming the serrations and you'll have very poor tool life in titanium. So the best option there is probably to stick with carbide.
Okay. And how do you ensure that the machining parts don't get hot?
Making sure you balance between the speed and the chip thickness is key. If that chip does get too thin or too thick, that's where you could see more heat getting transferred back into your workpiece itself. So that's where making sure to try and optimize for that chip thickness target based on your geometry. You're going to have to calculate out where you need to be at with your feed rate. But the goal is to have 80% of that heat being pulled out in your chip. But that's if the chip gets too thin, that's where you're going to see some of that heat getting transferred back into your workpiece.
Okay, great. And actually, I'm going to jump to, there's a question that's related to that. Somebody asked, I noticed that parts heat up after cutting material. Will this cause warping or shrinkage down the line after heat treating? So sort of a similar note there.
Well, typically the parts should already be through some type of heat treatment process before using the ceramic inserts. Generally, we're going to recommend machining on hardened steel parts or some type of alloy, HRSA that may already have been through a aging process that would have a higher hardness. So any type of heat that's generated can cause some sort of change in the material along that surface, which hopefully we try to minimize, with that chip thickness, controlling that.
Okay, thank you. We have a question here. What would be the surface footage difference when cutting MAR M247 between carbide tooling and ceramic tooling?
I think that would differ mostly with whether you're turning or milling it, because your turning speeds are still going to be somewhere in the 1,000 to 2,000 surface footage, where if you were milling, you'd probably be much higher than that. You'd be about double. So with carbide, you could be anywhere from just a couple hundred surface feet to turning it, you would be more like anywhere from 1,000 surface foot. And if you were milling, it'd actually be more towards 3,400 surface foot with WG 300 or 600, and about 2,600 surface foot with Excite 1.
Now, those type of questions are great to reach out to the tech team, calling in or shooting emails to us. We can help on those type of processes.
Sounds good. We just got a few more here. How do these ceramic tools handle interrupted cuts?
The best grade for the interrupted cuts would be our Excite 1. It has a tougher substrate, so it's going to be able to withstand the interruptions. With our whisker grades, they work as well. We have several grades that we plug into milling operations where it is at high interruption. Generally, though, kind of counterintuitive to what you would run with carbide tooling. With ceramics, you're going to want to understand what that interruption, the gap that'll be, and actually increase your speed by a percentage to help reduce that time that it's out of cut, just cutting air. So you're going to want to try and increase that speed in order to compensate for that. But ceramics can certainly be applied in any type of interrupted cut.
Great. We have a question from Poland here. Is machining 99% nickel content possible or not by whisker grade is the question.
An awful lot of nickel. I would probably say no. That's probably quite hard, right?
Yeah, although we should be able to, possibly with the whisker grades. It's probably something we want to look at, understand what the application actually is, whether we're looking at turning or milling, and trying to evaluate a little further. So certainly a great question. Reach out to the tech team here. We can try and make sure to connect you with the right sales engineer as well.
And we may be able to reference test reports from the past, whether or not we've machined that. Right off the top of the head, I can't quite remember, but we may have something on that.
Right. And here are a few more. Can more tooth tools compensate for lower RPM machines?
It would be more related to the diameter of the tool. So yeah, we would typically put more teeth into a larger diameter, but if we can run with a milling cutter that has a larger diameter, we could then possibly compensate for a machine that has lower RPM capabilities.
Great, thank you. And from the same attendee, another question. When does it matter applying coolant versus running dry?
So with coolant, especially with the ceramics, a continuous cut is preferred when you're using the coolant. However, whenever there's like a heavy scale or interruptions, we really don't recommend coolant because that introduces another challenge, which is thermal cycling. And thermal cycling causes the insert to go hot, cold really rapidly, which is not a good property for ceramics. So it would run dry for interruptions, and in a smooth, continuous cut, you'd be all right to use coolant.
All right. And we have a question here about sintering methods for ceramic production. The attendee asks, do you use hot press, hot isostatic press, or more advanced methods?
We use some advanced methods for our pressing of the ceramic products. Proprietary to us, so wouldn't want to disclose it during this kind of public space.
Got it. That makes sense. All right, we have some more questions still coming in here. So let's try to get through these. Does ceramic tooling perform better for turning compared to milling or vice versa?
Really just depends on application and grade. So, I mean,
material is going to play a large role in that as well. So, yeah, it's not to say that one application is going to perform better than the other. I think definitely in turning, there's plenty of applications where ceramic will be the best product. However, you do run into the restrictions if you're running with a smaller diameter that you're not able to achieve the speed required. Versus on milling, it's much easier to get to the target surface speed based on the diameter of the cutters.
Okay, great. And it looks like we have one more here that just came in. What kind of holders should we avoid with ceramic end mills?
So if you're talking about solid ceramics, definitely avoid your typical collet style or the blank on it.
ER style collets you're going to want to avoid.
Or the Weldon shank. Definitely want to stay away from those. So you'll want to look at using a shrink fit or hydraulic style. They're going to be your best option because those will hold the best concentricity for ceramic.
All right, thank you. Looks like those are all the questions that we received. Once again, I want to thank Beth, Martin, and Aaron from Greenleaf for joining us today and sharing such an informative presentation on this important topic. And I also want to thank you, our attendees, for your participation and all these great questions that came in. Thank you for those. We hope you found the content valuable and will join us again soon. And until then, remember that SME and SME Media are here to help you stay up to date on all things manufacturing. You can find links to podcasts, webinars, publications, and news by visiting us at advancedmanufacturing.org. Thank you.